Okay, we'll talk about the geometry finder system now. Most of SPI software computes geometric quantities for a given time. In other words, performs computations in the form x equals f of t. For example, at a given date and time, what is the spacecraft's altitude per kilometer? The geometry finder system does the inverse. Given a geometric condition, it finds the times when that condition is. For example, at this specific date, what is the spacecraft's altitude of Mars? That's the x equals f of t. Here we have an example of the kind of question that the geometry finder can answer within some time bands. When is the spacecraft's altitude between 50 and 100 kilometers? The geometry finder subsystem finds times when specified geometric events occur. A geometric event is an occurrence of a given geometric quantity satisfying a specified condition. For example, Mars express distance from Mars is at a local minimum. Elevation of the Cassini orbiter seen from Deep Space Station 14 is above a given threshold angle. Titan is completely occulted by Saturn. The Saturn phase angle is seen by the Cassini orbiter is 60 degrees. Each geometry finder search is conducted over a user-specified confinement window. And this is a term you'll see again and again. This is an input to the geometry finder routines. The confinement window is a time interval, or union of time intervals over which a search is to be conducted. And the result of a GF search is also a time window over which the specified condition is met. There are two kinds of GF APIs. There's Boolean event finding APIs. Boolean events are geometric conditions that are either true or false. Example, occultation, such as Phobos is occulted by Mars, or whether an item is in the field of view of an instrument. For example, Vesta is not in the Osiris instrument's field of view. Sometimes we call these binary conditions. And numeric conditions. A geometric quantity, and this is always a scalar quantity in the geometry finder system, has a given value, is within a given range, or has achieved a local or global maximum or minimum. Incidentally, although we have repeated references to ranges here, actually what the geometry finder interface allows you to do is use inequalities or inequalities relative to a maximum. You could ask whether an angle is within 5 degrees of the absolute maximum. Examples of numeric quantities are spacecraft altitude between x and y kilometers above the surface, angular separation of Titan from Saturn has reached the maximum within the search window being used. These are the high-level GF API routines. I don't know if I said this, GF is just our usual abbreviation we use for geometry finder. GF dist solves for conditions on observer target distance. You can also solve for conditions on illumination angles, on find times of occultations or transits, solve for conditions on phase angle, solve for conditions on coordinates of a position vector. So you could have a condition on latitude, longitude, range, or x, y, and z, for example. Determine whether a ray is contained in an instrument's field of view. Solve for conditions on observer target range rate. Solve for conditions on target body angular separation. Solve for conditions on ray body surface intercept coordinates, for example, the latitude or longitude of the surface intercept. Solve for conditions on some observer point coordinates. Solve for times when a target body appears in the instrument's field of view. And these are two user-defined quantity searches, one for user-defined Boolean quantity, one for user-defined scalar quantity. And these are available only in Fortran and C, and they are available, see, I believe they should be available in SpicyPy, but I've not checked. They're also available in JNiSpice, the alpha test Java toolkit. Okay, so Windows. We mentioned Windows before. The high-level GF routines return the search result as a splice window. The window specifies time intervals when the user's constraints are satisfied. A window is a span of time defined by a start time and an end time. Within that span, a time-ordered sequence of 0 or more time intervals, each having 0 or non-zero length. These intervals are closed intervals. The endpoints of the intervals are always considered to be included. Splice provides routines. Okay, so we're talking about Windows operations. You could do algebraic operations on Splice Windows. Splice provides routines to compute unions, intersections, and differences in windows. Also to contract each interval within a window by increasing the left endpoint and decreasing the right endpoint. And this is a useful operation for eliminating small windows that exist only due to round-off error and for making sure that windows do not exceed the actual times for which a condition is met. Now, why would you need to do this? Well, the geometry finder is solving for time windows. So the endpoints of all the intervals in a window that the geometry finder has determined are the result of a double precision computation and therefore have round-off error. So it may be the case that at the endpoints of the intervals where Splice is claiming a condition is met, the condition is not actually met. And you can solve that problem by contracting the interval slightly. So these Splice window operations allow you to search for multi-condition events. And here's one example. Here we have an initial confinement window. Well, okay, actually, this is not an example. This is an example of window operations, but not of working with multiple events. This is an example of using window arithmetic to produce a window, which is a window suitable for performing a search on. So we have an original confinement window. That's window A here. This window defines the time interval over which we're interested in performing the search. We have a window that shows the times of availability of reconstructed pointing. So we see that this pointing is available for these short intervals, the gaps between the intervals, and these small intervals come nowhere close to the coverage of the original confinement window that we're interested in. We also have an SPK availability window. By intersecting these two windows, we have a window that shows when both the CK data we're interested in and the SPK data we're interested in are available. And finally, we take this window and intersect the original confinement window and get the window of time where we can perform the computation we want because we have the data we need and these times are within our confinement window. All that is done with, these intersections are done with Splice window arithmetic routines. Okay, a little more on using time windows. Our search confinement window spans a time from, well, it doesn't span a time. It is situated between a start time and a stop time, end time. And its purpose is to confine the time bounds over which your search is to take place. So you can't search over an arbitrary time if you don't have, since searching is, I don't think I need to explain it more than that. Let's just go on. Again, GF uses Splice windows for input and output. Input confines the time bounds over which your search is to take place. And just to emphasize, we're talking about time bounds, but in fact, input is in many cases a real window with multiple intervals. It's not just a single interval. On output, you have the time intervals that meet the search criteria. There will be none, one, or multiple result intervals. Result intervals can be of non-zero or zero length. A zero length interval is simply an epoch, an instant in time. And here's just a graphical representation where this green represents the original confinement window, and this orange color represents the intervals in the output window. You see we have some continuous intervals and some intervals that are simply discrete, consisting of a single epoch, zero length intervals. The result, okay, so, go back for a second here. Zero length intervals are the kind of intervals you'd expect to see for times of singular events, such as apoapsis or periapsis. We've got a condition that's not just for one instant in time. The result window from one search can be used as the confinement window for a subsequent search. This is often a convenient and efficient way of performing searches for times when multiple constraints are met. The technique can be used to accelerate searches in cases where an initial fast search can be performed to produce a small confinement window for a second slower search. Now, there was a detailed example in the GF required reading. There's an example program at the back of the required reading in an appendix. That example program is called Cascade, and that shows doing a cascading search where first an angular separation search is done to cut way down on the time, the set of times where an occultation might be able to occur, and then searching over that window with a second search, searching for occultation. And that example demonstrates a 100-to-1 speed up that's achieved by using that cascading approach. So here's a little overview of how one would do something like that. In this case, we're searching for occultations of sun and moon, as seen from DSS 14. We first perform an angular separation search, and here's our original confinement window. We find times when the angular separation of these two solar system objects as seen from the observer is less than 3 degrees. And that's a small window. And then we search over the small window for occultation to see when the moon is actually occulting the sun. Because the angular separation search is much faster than the occultation search, the overall time it takes to do these searches is greatly reduced by doing this angular separation search first. GF documentation module headers contain complete example programs for each GF API routine. Now, the GF APIs are rather complicated typically, including the work it takes to set up a GF call by producing a confinement window, and in Fortran and C by declaring a result window. And so often the easiest way to use the GF routines in Spice is to look at these code examples and perhaps cut and paste some of the example code and then modify it for your own purposes. The GF required reading contains a lot of details. There's also documentation on Spice Windows and Windows required reading, and in the other functions tutorial, and API documentation for the Spice Window routines themselves. There are many more details covered in the online GF tutorial. You're strongly encouraged to look at this if you intend to use GF software. And here are a few examples of searches that can be done with GF. So I'm going to go through these quite fast. 5 times of apoapse, 5 time periods when a spacecraft is within a distance of another object, in this case, an object on the surface. So just one detail here. We talked about using SPK files for different kinds of objects that are non-traditional, not just spacecraft, but planets and satellites. Having an SPK file for the rover makes it possible to use it as an ephemeris object in the search. So you enable a lot of Spice capabilities for having an SPK file for something that seems like it could be just characterized by a single position vector. Find time periods where the range rate of a lunar reflector is seen by Earth station and it attains an absolute maximum. Find time periods when the angular separation of Mars to Mars reconnaissance orbiter and Mars opportunity rover position vectors is less than 3 degrees. Both targets are modeled as points. Find time periods when the angular separation of the figures of the moon and sun as seen from the Earth is less than 1 degree. Both targets are modeled as spheres. Occultation and transit searches. There are different kinds of occultations and transits that you can search for. You can search for angular transit, meaning that the object that's in transit is completely within the disk of the background body. Partial occultation, partial transit, full occultation, transit, sorry, that's a point-targeted occultation and an ellipsoid-targeted full occultation. SPICE will do accurate modeling of occultations and transits of an ellipsoid across an ellipsoid. So it does that carefully, and you can get accurate results as opposed to those that would be obtained using spherical models. Targeted field of view. You can ask when an object is the figure of an object intersects the field of view of a specified instrument, and the field of view shape can be any of rectangle, circle, ellipse, or polygon. Point targets are also supported. Ray in field of view. Ray could be appropriate for either the direction to a distant object like the star or to a point on the surface of an object if you have an ephemeris file for it. In any case, you can find times when a specified ray is in the field of view of an instrument. You could do a position coordinate search, in this case a position coordinate local extremum search, looking for times when the heliocentric latitude of the Earth-Sun vector expressed in the J2000 frame is at the local maximum. Position coordinate inequality search, here we're looking for time periods when the elevation of the DSS-13 to MRO spacecraft vector is greater than 6 degrees. Another position coordinate inequality search, find time periods when the lunar reconnaissance orbiter's off-nadir angle of the plus the axis exceeds 5 degrees. Find times when the planetocentric latitude of the sub-spacecraft point is 25 degrees. That's a case of equality search. Find times in which the planetographic longitude of given camera bore site intercept is minus 45 degrees. Another test for exact equality. Surface intercept box search, so you might want to find times when the surface intercept is within a given coordinate rectangle on the surface of an object. And in this case, you actually have to do 4 searches. You have to search for the longitude is greater than the minimum value, less than the upper value, the upper latitude value, and above the lower latitude value. And we can do cascading searches. Each one is more efficient than the previous one because the time intervals on which the search is conducted are smaller. Here's a case of a user-defined quantity extremum search. Here we're finding time periods when the angular separation of the geometric and apparent positions of time by apparent can be corrected for light time and cell aberration, as seen from the Cassini orbiter attains the absolute maximum. Okay. So a couple things about GF. The online tutorial has a lot of background information in the backup section. It explains the mathematics behind the searches that we're doing and how the root finding process works. And that's actually pretty important to understand. One thing that we glossed over here is the concept of step size. It's actually, in many cases, non-trivial to figure out what an appropriate step size is. And that you need to, in general, you need to know something about the geometry of the problem you're dealing with in order to pick an appropriate step size. If you pick a step size that's too small, your search is going to take a very long time. If you take a step size that is too large, you may skip over events, just miss them entirely, or you might see an event as covering a continuous interval where there's actually a gap in the middle of it, or multiple gaps in the middle of it, that were never detected because the step just stepped right over it. For the kinds of searches, the binary state searches that we described, that's for targeted field of view or augmentation, step sizes have to follow those constraints. The step size has to be shorter than the shortest event that you happen that you're interested in detecting, and it has to be shorter than the shortest gap that could occur within an event. For the scalar case, it's a little bit interesting. You can use a step size that's a lot bigger than the length of the event you're trying to detect. That might sound a little bit contradictory. What the scalar system is doing is looking for first times. It's looking for the times of local extrema of whatever your scalar quantity is, local maxima and local minima, and then it searches between the times of those the adjacent times of those extrema. So as long as your step size is shorter than the minimum time between extrema, the geometry finder search will work properly for scalar quantities. That means, for example, you could find an event that's 5 minutes long using a search that's 1 month, a time set that's 1 month long, if the extrema of the quantity you're looking for are separated by more than a month. Again, this is explained in detail in the GF required reading and in the backup material in the online version of this tutorial. But one of the main causes of confusion and disappointing results and mysterious results with the GF system is not using the proper step size. One other caution about step size, pointing of instruments is not the kind of thing the geometry finder system is designed to deal with very well. It works really well with motions of celestial objects and orientations that are continuous and have nicely behaved rates. But with pointing, with instrument pointing, unless it's pointing that has been defined in a way that's very smooth and well behaved, you typically do have to use very short step sizes in order to find the events that you're looking for. So it can be problematic to work with instrument pointing. Okay. Yes?
For the Bray in field of view, do you have to define the start, or is there a start catalog?
There is a start catalog capability within SPICE. It is not actually that much used. But what would normally one would do is to obtain the direction from the start catalog and use that direction vector itself as an input to SPICE.
So if you wanted to see a specific start,
you would not use SPICE to obtain the vector. Most likely, you would use the start catalog, whatever interface software it provides to get a vector of interest.